Hello, this is Prof. Nanius. This is a short video uh, to demonstrate a little bit of what a mini lesson would look like. And I'm going to be doing a very quick lesson on a topic that's important to us right now. And that is about COVID, the Delta variant. Well, not directly about the Delta variant, and the probabilities of being hospitalized if you're vaccinated versus being hospitalized if not vaccinated. Now, I want to make this clear. My analysis is not a professional level analysis. It is really a back of the envelope caliber calculation based on data that was already obtained. I'll put a whole bunch of caveats at the end of this little talk, which will be a couple, maybe 5-10 minutes, and we will get started. So we'll start by sharing screen. Now, I am a professor at Bradley University, which is in Peoria, Illinois, which is considered central Illinois. One of the major hospital systems in this area, health center systems, is OSF office, St. Francis, Order St. Francis. Now let's take a look. Go to share screen, and data has been collected on COVID hospitalizations, and data has been compiled on vaccinated versus unvaccinated. And we can see that right here, these are the COVID-19 hospitalizations. This is based on 14 of 15 OSF hospitals reporting. Now, I want to make it clear, when you do analysis like this, it's important to know what percentage of the population is vaccinated versus what is not, what population is not vaccinated, or else or else this could be very deceiving. So I will just add, based on Central Illinois statistics, about 50% of the population is vaccinated. And that does make a difference, and here's why. Because if you had these numbers, let's say you had 90% of the population was vaccinated, and you saw numbers like this, the green are the fully vaccinated who are hospitalized and the blue is not, then this would really speak extra strongly about the efficacy of the vaccine with respect to hospitalizations. But that, sadly, we don't have 90% vaccinated. We don't have 80% vaccinated, although our over 65 population is about 80% vaccinated. We'll talk about that issue just a little bit later. But about total of populations around 50%, roughly the same as Florida. Okay, so we have that. And notice, if we just focus first of all on the total in hospital for COVID reason, we see that 23 are fully vaccinated, and we see that 100 are not vaccinated. So from this, we can calculate something called the efficacy of the vaccine. I know that's from an experimental trial, and this is just data in the field, but let's just go ahead and take a look at that. We'll go to our ladybug here. And I wrote this down just so I didn't forget it. And the way efficacy is calculated is, what you do is you take the percent unvaxxed that's in the hospital minus the percent vaxxed in the hospital. You take all of this and divide it by the first number here. And this will be the efficacy. Now, another way of writing this down, if you do a little bit of algebra, if you notice right here, this denominator, and I know it's unclear the way I wrote it right here. So let's write it in something resembling math. Percent unvaxxed minus percent, well, U, we'll call this V, divided by percent U. So this looks more like a fraction. Another way of writing this, if you really want, is you can break this fraction up and write it as 1 minus V over U, and this will be the risk ratio. Right, risk of being unvaccinated. Now, from what we had, the numbers here, they actually work out quite well because technically speaking, we need a percent here. But since we're talking about a population of 123, we'd have the same denominator in all of these, so we can dispense with the denominator and just write it thusly. 100 minus 23 over, in this case, 100, because 100, let me go through this again. 100 is the unvaxxed in hospital. 23 is vaxxed in the hospital. So putting into this formula, it will be 100 minus 23 divided by 100. That's sort of nice because what we end up getting is we end up getting a 77 over 100. So the efficacy is 77%. Okay. So that's really the how good the vaccine is in preventing people being hospitalized. Now, there are some caveats here though with this, and I can see some people getting upset. We're saying, well, wait a minute, isn't the protection against hospitalization much greater? So let's put in the caveats here. So this caveat, and by the way, yeah, so here's the caveats. Is one, get to get a better feel, to get a better picture, this ought to be broken down by risk. For example, and what I mean by that is that it is possible that the vaccinated people in the hospital could be all immunocompromised or old, and you could have a lot of younger, healthier people who are unvaccinated and in the hospital. So to really break this down in more detail, you ought to break this down by risk category, or by age, or by immunocompromised versus not immunocompromised and all that. But this right here is a very, very rough and dirty for the whole population taken as a whole. Okay, still pretty good protection, but it's not the suit of armor that we want to, what we'd like to imagine. Now, the next thing is, let's go ahead and take a look at this statistical test. Now, I think I should go back to the ladybug and saying what about a statistical test. Where H naught would mean vaccines, no effect. The alternative hypothesis is that there's an effect. And the population here is 123. And the hypothesized probability is 0.5. Because if the vaccine had no effect, you'd expect roughly equal numbers. So let's check this. the null hypothesis, no effect, versus the alternative hypothesis that there's an effect. So if we go ahead and run this through a binomial calculator, so let's go ahead down here, close this up. We run this through a binomial calculator. What we see, there's 23 vaccinated people out of 123, with the null hypothesis p being 0.5. And we get the p-value is right here. P-value is 6 times 10 to the minus 13. That's pretty good. That's rather impressive. Rather an impressive statistical test. So here we reject H naught. P equals 6 times 10 to the minus 13. Now that's pretty good. Now just to review what a p-value means. What a p-value means is that if it was really true that vaccines had no effect, you know, it's 50-50, then you'd expect to see this sort of disparity basically that percent of the time, or the p would be 6 times 10 to the minus 15% of the time, which is okay. Good luck with that. I think that's a, I think that's a reject the null hypothesis. Now, in order to do this, let's go ahead now and take a look at the in the ICU. So let's calculate the efficacy for ICU. Now in ICU, again, we can do it this way because it's about 50% of the population is vaccinated. It's actually slightly less. You have 2 that are vaccinated, 32 unvaxxed. So if we do the calculation, 32 over 30, I'll put the denominators in this time. As you can see, the denominators are just a waste of time. Up helps if you write this down. 30 over 32. That's pretty good, right? Got my handy calculator here, but that's 15 over 16. So that's 93.75. So the efficacy versus with respect to ICU is 93.75%. That's pretty good. All right. And again, same caveats. The caveats is that this really ought to be broken down into risk category. And I think what you'd find is that you'd find the efficacy of the hospitalizations and the efficacy of the ICU higher than what's shown. But this is sort of lumping all the population together. I have one. Now, ventilators, well, that's 100%. I don't have to do the calculation there, right? Now, again, this is just a small central Illinois sample, but I think it demonstrates the effectiveness of vaccines, but it also makes it clear that vaccines are not a suit of armor, or not perfect armor. You can still get COVID, even if you're vaccinated, and yes, you can still end up in a hospital. It's just that the probability is a lot less. So thanks for watching.